Hello, I'm Soussans, and today I'm presenting our work on sparse and structured Hopfield networks in collaboration with Vlad, Daniel, and Andre. Recently, modern Hopfield networks got famous due to their links to attention mechanism and associative memories, and motivated by this, in this work we extend this to a broader family of energy functions via Fenchel-Young losses. These losses have as a particular case sparse transformations, which do have margins, and due to their sparse nature, exact retrieval can be deduced, which leads to Hopfield networks with exact convergence to single memory patterns and exponential storage capacity. We further extend through structured spaces via SparseMAP, which can also be deduced from Fenchel-Young losses, leading to retrieval of pattern associations. Finally, we conduct experiments on synthetic and real-world data. We start with classical Hopfield networks, which are generally binary, and their role is to retrieve memory patterns based on a noisy queue, as can be seen in the first figure. They fail to provide consistent results, as they lack a strong storage capacity, leading to mixture of patterns or metastable states when many patterns are stored, as can be seen in the second figure. For this reason, Wormsauer et al. Introduced modern Hopfield networks as a generalization to continuous states. In fact, considering a matrix X of n memories and a query Q, they define the energy as a sum of a log sum X controlled by an inverse of temperature, beta, and the L2 norm of Q. The update rule is similar to transformer self-attention, and memory patterns are close to attractors. However, there can be mixtures of patterns retrieval, leading to metastable states. Also, exact retrieval is only approximate due to the softmax nature. In fact, for some cases, I beta must be chosen to avoid these metastable states, as can be seen in this figure. One possible solution is to add sparse transformations that have a similar role of an increasing beta. In this paper, we aim to address these questions. More concretely, can we design high-capacity continuous space Hopfield networks with exact retrieval? Can we make them less sensitive to temperature? And can we extend them to handle structure? To do that, we start to define what is a Fenchel-Young loss. Fenchel-Young losses assess the compatibility between the ground truth Q, which is in a simplex, with a vector of scores Y. We can then consider an omega, which is an argmax regularizer, and its convex conjugate. Then the Fenchel-Young loss can be expressed in terms of these variables by this equation here. The gradient map, which is defined by the regularized prediction function at Y, which is simply the gradient of the convex conjugate, reduces to several cases such as the softmax and cross entropy loss when omega is a Shannon entropy, alpha max loss when omega is a Tsali's entropy, or even alpha normax transformations when omega is a norm entropy. They have interesting properties such as these Fenchel-Young losses are always greater or equal to 0, and when equal to 0 the scores correspond to applying the regularized prediction function to theta. Additionally, they are always convex on theta. One crucial definition in this work is the definition of margin, where a Fenchel-Young loss has a margin m greater than 0 that measures how far a theta is from its maximum. Particular cases of losses with margins are the alpha max and the alpha normax. Formally, we are now able to define the Hopfield-Fenchel-Young energy induced by a convex omega as a sum of a convex and a concave term. This is expressed in terms of the Fenchel-Young loss, and this energy recovers modern Hopfield networks as a particular case. The Hopfield dynamics are similar to modern Hopfield networks, but now with a regularized prediction function instead of simply the softmax. In this slide, we can define the separation of a pattern by measuring how far a given pattern xi is from the remaining patterns. Then, if the margin is lower bounded and the patterns are normalized with radius m, any epsilon close query to the stationary point of the Hopfield-Fenchel-Young energy will converge to this point in one single iteration. Furthermore, with probability 1 or minus p, the network can store an exact retrieve an exponential number of patterns in one iteration if an epsilon perturbation is upper bounded. In this paper, we also introduced structured Hopfield networks. This follows the same formulation, but now with a simplex replaced by the marginal polytope, representing a structured space. We consider two cases. The first is a case subset, which favors top k retrieval. The second is a sequential case subset, which promotes consecutive items to be both retrieved or neither retrieved. This can be done with a SparseMAP. with exact structure retrieval to pattern associations, leading to Hopfield dynamics with a SparseMAP function. You can see the paper for more details. In this figure we show visually our methods. For alpha endmax, the greater the alpha and the greater the beta the sparser the distribution gets. For alpha normax, the greater the alpha and the greater the beta, the more evident the uniform distribution becomes. For SparseMAP case subsets, we see the behavior described earlier, which favors top K retrieval. Formally, we are now able to show our results, and we start to show trajectories and energy contours for synthetic data. We can see a similar behavior to what was described before, where for the endmax going from the left to the right or increasing the alpha, this method tends to converge to single memory patterns. In the rightmost columns we show normax for 2 alphas, 2 and 5, and we can see that for larger alphas, alpha normax favors retrieval in the uniform distribution over the memories. Here we show basins of attraction for each memory point, and we can see a similar behavior to the previous plot, but here it's more evident the presence of more attraction areas with colors as alpha increases for alpha endmax. 2 normax has a similar behavior to 2 endmax, and in 5 normax we can see the white areas where there are no attractors in the areas between the different patterns. We also conduct experiments on capital K multiple instance learning, where a bug is considered positive if there are at least capital K positive instances. As expected, SparseMAP with lowercase k subsets achieves best performance for lowercase k equal to capital K. You can see the paper for more details and more experiments and datasets. Additionally, we conduct experiments on text rationalization, and here we show the produced rationals. Italic corresponds to the human rational, while yellow highlight corresponds to the model's rational. Sequential case subsets achieves an almost perfect produced rational with contiguous nature, while case subsets produce a rational with tokens spread across all text, which is not very good. We also show task performance results, and comparing to strong baselines, our proposed methods achieve equal or slightly superior performance for all datasets. Moreover, sequential case subsets outperforms all baselines in terms of overlap with human rationals. You can see the paper for more datasets. Finally, as conclusions, we present a unified framework for sparse and structural Hopfield networks. The core result is a connection between margin property of Fenchel-Young loss and sparse Hopfield networks with exact retrieval conditions. We extend this framework to incorporate structure using SparseMAP transformation for retrieving pattern associations, and we empirically evaluate on multiple instance learning and text rationalization problems. Thank you.